Isn't it? Everyone all good with that? It's good. Well, welcome everyone to another introduction to astronomy. Thank you for coming up. Another cold winter's night. So this image here is one of the famous images taken by one of NASA's most recent and advanced space-based observatories, the James Webb Space Telescope. And have you ever thought to yourself or been in discussion with someone like all the media and press and hype around it, what makes it so special and unique, and what sort of discoveries is it making? And if so, because a lot of people have asked me that, and I've thought about that a few times myself, you're in luck, because today's talk is the James Webb Space Telescope Unique Features and Discoveries, where we'll discuss and learn about what does make the James Webb Space Telescope so unique and special. We'll also address the questions of what is it showing us that we haven't seen before, and how this changes our view on the universe, the implications of what they're finding. And if there's one message you take home tonight, it is this: the James Webb Space Telescope is changing our view and understanding of the universe. And that's what you're going to see tonight. Take that message home. Okay, so what makes it very special and unique? Two main factors. Its size, which we're going to address both these, its size and the fact that it's designed for infrared observations. So this is a full-scale mock-up model of it on the front lawn of the Goddard Space Center where it was developed. And there's about 400 people, I think I've counted in that picture. Look at the sheer size of it. It is really huge. And what makes it so special is that mirror, 6.5 meters across. The size of that mirror is what makes it so special. That's half the size of this room. Imagine that gets launched up and it's sitting up there in space. And that's what gives it its power. If you go to buy a telescope, don't get roped into things about magnification. That it all comes down to the size of that primary mirror. That's how much light it can collect, and that is what enables it to observe faint, small and distant objects in high resolution. It comes down to that mirror, 6.5 meters. In comparison, contrast, Hubble's 2.4 meter. So there you go. And I'd put this up here just to illustrate that. These are all in the infrared. We'll talk about infrared shortly. So these are all in infrared. It's the same star field, but by different telescopes. Here's the WISE telescope, 40 centimeter primary mirror, just a few blobs, isn't it? You go to Spitzer in infrared, same star field, 85 centimeter. Those blobs, we've started to see a little bit more detail on those blobs, but they're still really blobs. Look at the James Webb, 6.5 meter. Just look at that resolution, and that's the same star field. So the point of that slide is to illustrate the importance of just increasing that size of the mirror. You suddenly see everything, small objects, faint objects, and more distant objects in high resolution. So that's size. So how about infrared? First of all, just a little bit of basic introduction is that light, as we see it, it's made up of alternating electrical and magnetic fields, alternating, what they call electromagnetic spectrum. And we just see visually with our eyes here, let's just get this here, we only see a small, very part. Our eyes, our retina, have adapted and evolved to work optimally in just a very narrow range of that spectrum, because our sun emits light predominantly in that part of the spectrum. But if you get more, you go to shorter wavelengths. Here's our wavelengths down here in comparison. As you get shorter wavelengths, you get more energetic photons of light. Ultraviolet, of course, gives you your skin cancers. Then if you break your bones and get an X-ray, more potent again, and then you go up to your gamma rays. And moving down the other end, here's your infrared, which is a lot of remote controls and stuff, so it's a lot less energetic, it's safe. Then you're going down to longer wavelengths, a bit lower energy, microwave, and your radios. And it's this infrared zone here that I've highlighted here that the James Webb is interested in. So the other thing I'll just mention here too is that infrared light is absorbed by water vapor in the atmosphere, and that's why to get decent observations in infrared wavelength, you've got to get above the atmosphere. So you've either got to be high up in the mountains or preferably in space, well above the atmosphere. So what sort of features does the James Webb have to enable it to be really good in the infrared? First of all, its location in space, so it's above the atmosphere, but it's actually 1.5 million kilometres out away from the Earth at a place called Lagrange Point 2. Sun here, Earth here, Lagrange Point in this direction, and a direct line between them, and it's about 1.5 million kilometres out. And it's a nice gravitationally stable area where the gravitational pull of the Earth and the Sun perfectly matches the orbital motion around. So it keeps there nice and stably, but also it can direct itself with this large sunshade here. This sunshade is the size of a tennis court. It comes in 5 layers. It's made of Kapton, which is a very good thermoplastic, and it's able in just one clean sweep face away with the Sun and the Earth behind it, so they don't get contamination, if you will, or noise in terms of light and heat from the Sun and the Earth, because light and heat, you do not want it. That's noise. You're interested in really fine, sensitive infrared observations out in space. So that's the purpose of being out in space that far out, and the sunshade. The mirror coating, you'll notice it's a gold colour. We always think of mirrors as being silver, and that's really optimal for optical wavelengths or visual wavelengths that we see in. But for infrared light, it reflects best off gold. So they've got a gold mirror. All their instruments and their sensors, their CCD sensors and all their instruments are specifically designed to optimize for infrared absorption. They have a camera for imaging, and they have 4 spectroscopes. A spectroscope is what splits light up into either finer wavelengths to help determine the temperature of something, its composition, and its velocity to or away from us. So they've all been specifically designed for the infrared. And cryogenics, it's kept really, really cool, at least minus 220 degrees Celsius. You know, we think it's a cold day when you get to 0 or 20 degrees. It's minus 220 degrees Celsius. That's what the temperature they keep the telescope at. Why? Is because, as I've just mentioned, it's got instruments and sensors and so on. They're all electronics. What do electronics produce? Why do you have holes in the back of your TV and all your computer and stuff? It generates heat. And heat is infrared wavelengths. It's noise. You do not want heat off your instruments, contaminating your observations from far away. So it is cryogenics as well. And it's those properties or features in the telescope that make it really, really good at infrared observation. So why do you want to look at infrared? 2 main reasons. First of all, it allows you to see through dust. We all know if you've got something in visual wavelengths and you throw a whole big stack of dust up, it obscures it. Visual wavelength light cannot get through dust. The dust obscures it. But infrared light just cuts straight through dust, so you can see what's behind a big cloud of dust in infrared wavelengths. And the other thing is you can see long distance. You might think, really? How does that work? Well, the light from the very first stars and galaxies early in the universe, they would have been emitting light in the visible, a bit of ultraviolet light, but at this end of the spectrum. But over the last 13.8 billion years, the age of the universe, the light's been happily travelling along through the universe, but the universe has been busy expanding. So those nice little wavelengths of light over the last 13.8 billion years have been quietly getting stretched out into longer wavelengths. As you see here, hello, they now appear to us in infrared wavelengths. So suddenly we can see through dust, and you can see at much longer distance back into the early stages of the universe. You might think, okay, well, that's great. What can I see? Well, it means you can see new stars, as we'll so very shortly. They form inside big cocoons of dark dust. They can now straight through them and have a look at it. Stars, dying stars up to about 8 times the mass of our sun. When they die, they get, once again, they get enshrouded with thick dust. We can see those now. Early galaxy mergers, so that's very important to see how the early universe behaved. What were those first stars like? What were the first galaxies like? How did the merging process go on? They can now, because they've got that high, what they call, it's called redshift when you're looking at the infrared, longer wavelength. The light's been redshifted, so you can see that clearer. And also, suddenly, we've been able to locate and identify about 5,000 exoplanets with the Hubble and other telescopes and so on, and Kepler and TESS and the likes. But that's as far as they can go. They can they know that the planet's there, and they know a little bit about its size and its mass and its density, but they don't know much about its atmosphere. Suddenly the James Webb can analyse light going through the potential atmospheres of these exoplanets. Exoplanet, by the way, meaning a planet outside our solar system. It's going around another star. And suddenly the James Webb can have a close look at it if there's an atmosphere there. And if there is, everything in an atmosphere jiggles. Molecules, chemicals, everything in the universe is just jiggling around. When it jiggles around, it emits light. And all those chemicals and molecules that tend to hang around an atmosphere, when they jiggle and they emit light, that light's usually in the infrared, James Webb. So it can tell the contents of an atmosphere in a faraway exoplanet. So it's those two features that make it special. Now I put this slide here to illustrate how great it is at cutting through dust. This is an image taken by the James Webb. It's of the Pillars of Creation, which is just a small part of the Eagle Nebula, aka M16. And it's taken by the Hubble. This is in visible wavelengths, and you can see our illustration here. There's new stars being formed in here. And see what I mean about these regions where new stars are forming? They're cocooned in thick, dense, opaque dust. You just can't see what's going on. Now, the Hubble just dips very deep, just very slightly, just dips into infrared wavelengths. But even so, look at the difference. It's all, those pillars are almost transparent. Suddenly, you can see dozens and dozens of stars in those pillars that were completely opaque beforehand. So that slide beautifully illustrates the power of infrared astronomy. And this is just the Hubble at a small, relatively small mirror, 2.4 meters, and just dipping its toe just slightly into the infrared. Okay, so that's what makes the James Webb special and unique, and it's good size for high resolution and faint, small, distant objects, and it can see in the infrared, cut through dust and look back to the early universe. There are 5 fields, predominant fields of discoveries that the James Webb has been working in. So I'm going to work through these 5 now, and I've just tacked on another couple at the end of it as well. That's sort of interesting, more recent research. So let's have a look at the start of new stars forming. This here is a part of the Carina Nebula, got known as the cosmic. Normally you can see these big cliffs here of dust and stuff, and there are literally hundreds, if not thousands, of new stars forming that would not be visible. So what I'm going to do briefly, let's have a look at the Hubble picture. Before James Webb, that was our best picture of the cosmic cliffs. You see, look, all this area here, it's just all thick, opaque dust, isn't it? Just dense, dark dust. You really can't make out. A lot of these stars that you can see here are actually probably foreground stars. So you can't see what's going on. Okay, look at that now. Let's go back. Woohoo! Look at the contrast, the difference in the detail from the James Webb. Suddenly you can see, through all the dust, what little bits of dust you can see all the intricacies that are in it as well. So that's great. Let's have a look. In these little areas that I've highlighted, there's a few of them. I've just highlighted 3 of them here. So you can see like sort of more streaky patches, like gold streaky patches in here. And those are protostars that are forming, that are completely enshrouded in dust. Let's have a close look now at the James Webb images of some protostars. Here's one. Now, normally, this whole area, this whole photographic area, if that was in visual wavelengths, all you'd see is just a big mass of dark, dense, opaque dust. But look what the James Webb can see. So this is a young star that's forming. This is what our sun would have looked like when it was 100,000 years old. Just like that. So it's the protostars come in 4 classes, 0, 1, 2, and 3. 0 being the very, very most earliest stages when it's really, really covered in thick, dense dust. So they sort of really haven't been able to view inside them at all. And when this big molecular cloud of gas and starts condensing down to itself to develop a new star, and it starts rotating faster and faster and gets denser and denser, as it accumulates more material, there's a lot of charged particles in that material, so it develops stronger and stronger magnetic fields. And with its rotation, which is going faster and faster as it contracts down, the magnetic field starts spinning faster and faster, and the magnetic fields send out from its poles, twisted magnetic field lines out from its poles. And with those magnetic field lines, all your charged particles get sent out at huge velocities. So they call these bipolar jets of material. And they start slamming into all the other gas and dust and the other material that's out there. And you can see here, notice all the bow shocks here, little knots and filaments going on. That's all just high-speed material getting directed out at huge velocities, just ramming into the material. So once again, they can study that, get a better idea of temperatures, velocities, composition, what's going on. Up till now, that's all been enshrouded in thick dust. It's like most stars, they eventually develop a protoplanetary disk with planets form. You can see these two, just to the right of my dot there, you can see two white areas, looks like the buns of a hamburger, and see the little dark strip in the middle. Right in the middle is that little, just tiny little dark strip. That's the protoplanetary disk, and that's where your planets are going to form in there, full of material. So, what implications does it have? It's going to give us a better understanding of how stars form. In particular, what factors promote star formation, what factors inhibit star formation, what factors determine how many stars you're going to get from a cloud, from a big cloud of gas and dust. What sizes will those stars be? Those are the sort of stuff that they're really interested in, that they can now start looking into this. It's going to take years to pull a lot of this data out, but you can get the flavour of where it's all going to be heading. Now that was taken in near infrared. There's different grades of infrared. There's near, and you go to mid-infrared, and then you go to far before you hit those microwaves. So this one's taken by James Webb's MIRI, or the mid-infrared range. And they're able just to have a look and get a look at different types of dust and stuff that's going on, as opposed to cutting through the dust. And here's all your bipolar jets and your shock waves going on. Blue is what they call PAHs, or polycyclic aromatic hydrocarbons. And they are a complex form of hydrocarbon that is very important. Well, it's actually, you can get it on Earth, it's a form of soot. It's formed from oil and coal, the burning of oil and coal and so on. And it's thought to be very important, it's thought to be ubiquitous throughout the universe, but really important for the formation of planets and life in particular. So you can see all these complex polycyclic aromatic hydrocarbons here out in blue. Red is just heated gas and dust, it's extremely hot temperatures here. And white is a mixture of everything. There's bits of carbon and neon and silicon and all sorts in there that's getting condensed down. So that just gives you an idea of the sort of stuff that they can see behind these thick clouds. All okay, Eric? Yeah.
Can you give me
Yeah.
Let's start charging it.
Okay, what do I do?
No, you just keep speaking.
So speaking into here? Yeah, all good.
So, Chris, can I just ask?
Yeah, Tom, yeah.
So, I presume most of the material that's around stars is hydrogen and helium, but that doesn't obscure, that's not dust, that's not obscuring that.
There's a lot of dust in there too, actual dust particles in stellar space, yeah. And you're talking big distances, you're talking a light year or two, each of those bipolar jets. So it's quite dense, but you're right, 98% of the universe is hydrogen and helium, but there's sufficient dust in there over such big distances you're talking to obscure.
So the hydrogen doesn't obscure the light?
No, it's the dust, yeah, but quite correct. So let's look at old dying stars. Now this is called the Southern Ring Nebula, and it's taken by the James Webb. And old stars, when they die up to about 8 solar masses, they spend the last few 10,000 years or so of their life just gently pulsating and expelling their outer layers of gas and dust to expose their core. But just taking a look at this now, prior, that was the Hubble's best image of the Southern Ring Nebula. So it looks a bit blurry, you can sort of roughly make out what's going on. It's 2,000 light years away. Okay, let's go back. Look at the contrast, the difference, the detail you can see in there. So eventually all these layers get expelled and it leaves behind a central core of oxygen and carbon, known as a white dwarf. Really, really high temperatures in there, into tens of thousands of degrees, and that illuminates, sends out ultraviolet light, and it illuminates and causes all this other gas and dust out here to glow, or a lot of the gases fluorescing. And what astronomers are able to do with all this detail from the James Webb Telescope now, is they're able to go back through all these layers and once again examine each individual layer. I count about 8 different layers in there. And once again, composition, temperature, velocity, and if they extrapolate backwards, they can get a better idea of 3 things. A, the composition in the layers of that original star before it started pulsating and shedding itself. 2 is the whole expulsion process of sending material up. And the other one is that material then goes out and enriches the interstellar medium, all the space around it, to then be incorporated into the next generation of stars. So they're able also to study that whole enrichment process as well, just through having this sort of detail going on. So you can see how the implications of images like this. Once again, the mirror gets involved just to have a different look at some of the different types of dust, and they've colour-coded this such that dust is in red and all your hydrocarbons in blue. So once again, they could get a lot more information from there. The other thing was in the mirror, slightly looking at it in slightly deeper mid-infrared range, suddenly instead of over here, you see one point of light, one star, that's your central core, but look, they actually found there's another one, it's actually a binary star system at the centre of that. They would have never have seen that without that A, that high resolution, and B, being able to look into that mid-infrared. So that's new stars, old stars dying. Yeah, how about galaxy mergers? They're getting some wonderful views now of galaxies just further out that are lovely, sort of starting to merge and looking at the process of it all. And this is called Stephan's Quintet. And it's a galaxy cluster about 300 million light years away. And there's 5 galaxies. There's 4 of them here. These ones are all together in the same region, 300 million light years away. This one here is about 40. This one's actually in the foreground. We're not meant to be looking at this one just right now. It's these ones here. But you can see these are starting to merge. And when galaxies merge, they don't just come together like that. They sort of, under the force of gravity, come together, but there's motion going on. So they tend to do a little dance. They do a bit of a swing by and come around like that and then have another swing by. This happens over millions of years. And eventually they get into a dance and a swirl and they merge together like that. And in that process, they get distorted. And they also, the compression of all the gas coming together, it merges between galaxies, causes a lot of compression, which in turn triggers a lot of star formation, what they call starburst regions. And you can see, once again, what stars glow very well when they're first forming in these infrared wavelengths. And look, you can see all this star formation going on. All these are called tails and bridges, these little bit of dusty bits here. And that's all material from the galaxies, just all interacting with one another as they swipe past. And the importance of this is that the general theory is that mergers would have occurred more commonly in the earlier parts of the universe, when the universe was younger, there was more galaxies, and it was more crowded. So it makes sense there would have been more mergers going on. But we haven't been able to look far enough back or in enough resolution to fully understand the process. And suddenly, look at this. You can understand this whole process a lot better. Now, as a bonus, in the background here, you've got thousands and thousands of distant galaxies. So they're not just going to go, oh, that's a pretty picture. No, they'll be pulling that apart and looking at all of those galaxies, getting all the information they can. And the other thing is, there's an active supermassive black hole right in the middle of that galaxy there. Supermassive black hole. You've probably heard of just your basic black holes or stellar black holes. They are where a large star greater than 20 times the mass of our sun, it's at the end of their life, they stop nuclear fusion in their core, and the outer layers the core starts collapsing in onto itself. The outer layers start collapsing in, bang, 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 hit and rebound off that core and go supernova with a big supernova explosion. And the core collapses into itself, and it's just sufficiently dense and compact enough whereby the escape velocity is greater than the velocity of light, so not even light can escape from it. you have a black hole. That's called a stellar black hole, and they can go up to about 100 stellar solar masses. So then there's another class of black holes called supermassive black holes, and they are millions, if not billions times the mass of our sun, and they reside in the center of most decent sized galaxies, have a supermassive black hole in them. Our Milky Way indeed has one. It's about 4.2 million times the mass of our sun. That resides there. It's called Sagittarius A star. And it's what we call inactive, or another way of looking at it, if you think in the context maybe like a volcano, as opposed to being active, it's dormant. It's not extinct, it's dormant. No material is going past it, so it's not chewing it up and spitting material out. So it's dormant. So it would be nice to be able to study an active supermassive black hole where they were believed to be a lot more common in the early universe, but see one reasonably close up and actually analyse what's going on there, how it's feeding off its material and how it's spitting material out. And indeed, they have one here as an extra bonus in this one here. It's about 24 million solar masses. And just having a closer look at that, here it is here, and the spectroscopy that uses the light, as I mentioned that earlier on before, that's able to split light up even more and give you an idea of what's going on it. And there's a big surrounding cloud of gas and dust around the supermassive black hole, and they were to analyse that with the spectral lines. It shows a lot of dense hydrogen gas and grains of silicate dust, in other words, sand. The jets that are shooting up from the edges of it, shooting out here, able to do spectroscopy on that, and as you can see here, array of things, just a multiple mixture of various elements, argon, iron, neon, sulfur, and oxygen, and so on. And this is all valuable information for learning how active supernova, or rather active supermassive black holes, which are more common in the early universe, but this is one they can examine reasonably up close with high resolution and get a better feel for what's going on. This is all because of the James Webb. This was in the newspaper about 2 or 3 weeks ago, and it's called The Penguin and the Egg Galaxies. It was just highlighting some of the abilities of the James Webb. So this was released just last month, and it's two galaxies. This is nicknamed the Penguin, and this one's nicknamed the Egg. But this is a elliptical galaxy here, small elliptical galaxy. This one here, they've started interacting probably about somewhere between 25 and 75 million years ago, and there's about 100,000 light years between here. Put that in perspective, our Milky Way, our entire Milky Way is about 100,000 light years across, but our nearest relatively large galaxy, the Andromeda galaxy that we have started merging with, it's going to happen in about another 5 billion years' time. Winston Peters will still be in Parliament. It starts colliding, but that is 2.5 million light years away. So these here are only 100,000, so they're relatively close. So they started the merging process, but to give you an idea of how distorted it is, the beak of the Penguin, that was once the central bulge of the spiral galaxy. Look how distorted the whole thing is. And these little blue, see this upside down U shape here, of fuzzy stuff here, that's all material between the two galaxies that are starting to get mixed up and merged together. And the other things you'll notice, look at all this orange here that's going on from in infrared wavelengths. That's all new star formation, that's starburst activity. Just because of the compression and the distortion that's going on, it's just triggering star formation, just going crazy. There's a party going on in this galaxy, a star party, new meaning of the word star party. So it's a full-on star party going on here, as you can see. So once again, this is sort of detail and resolution that they haven't had prior to any of this, because high resolution and infrared wavelengths. This is just a lovely picture, just comparing the same galaxies. This is in the Hubble and optical wavelengths, so you can just see all these all these dust lanes going from here, thick, dense, opaque dust, and suddenly you can see through the dust here in infrared and actually see the stars forming. And they will no doubt blow that up further and get a lot more data out of that. Okay, so it's galaxy mergers. How about the first stars and galaxies? Wouldn't it be good to have a look at those? Because if you want to understand how the universe formed, how it developed, and how it evolved, you need to understand the stuff. You've got to understand how the first stars and galaxies formed, when did they form, and how did they grow and evolve. That's really important. And at this stage, I just want to introduce the concept here. It's a tool, a natural phenomenon that astronomers use to magnify things in the background and see really long distances. It's called gravitational lensing, and it was predicted in 1915 by Einstein's general theory of relativity. It predicted this. And his theory suggested that what we experience as gravity is not so much a whole new force, it's just that mass distorts the fabric of space-time, which bends light and everything, and that we perceive as this attractive force going on. But it also predicted that if you get a big clump of mass, like a big cluster of galaxies, a huge amount of mass here, it will warp the space-time around it in a lens effect to essentially create a lens called a gravitational lens, whereby if you're looking in a line like that, in alignment, and you want to see something in the far distance here, the light, this distant galaxy light, will diverge out, come to its lens, and then converge and focus in on your James Webb Telescope. So you're able to see a lot longer distancing. And that's called gravitational lensing, natural phenomenon, and it's what astronomers use as a tool. Yet multiple magnified views, distant stars and galaxies. So let's have a look. This is a lovely deep field image from the James Webb. They've got an area of the sky about the size of a grain of sand held at arm's length into the sky, apparently blank bit of sky. 12.5 hours worth of exposure time, and that's what they saw. It's estimated there's probably about to 10,000 galaxies in there. So what they did, they knew there was a nice big cluster. SMAC stands for Southern Massive Cluster Survey. They did a nice big survey of the southern sky, worked out where these big clusters were. Look at one of these. They decided, look, the cluster 0723 was the one to look at. That's 4.6 billion light years away. And see these galaxies right in the middle. They're part of the cluster there. These galaxies just in here. But what it has done is magnified a gravitational lens all these distant galaxies in the background. See all these ones that are distorted, these red distorted ones that are magnified and distorted? They are 13.5 billion years ago, look back time. Don't get confused, by the way. There's light years distance, and then there's look back time. When you get to these big distances, you tend to drop, that's so many thousand light years. You look back and look back time. So you're looking back, the universe, remember, was 13.8 billion years old. So you're looking back here, these galaxies are only about 300 million years after the Big Bang. And that's about 2% of the age of the universe. So that's really cool pictures. So they can analyse all these galaxies and stuff. Indeed, they have started doing that. And there's one in particular they hear. This is the most, currently, for the record, of the most distant galaxy that they have identified. And it's called JHGS Z14-0. The Z14, Z is an abbreviation for amount of redshift, how much the light's been shifted. So a redshift of 14, is when the universe was 13.5 billion years ago, 300 million years old, in other words. So here, this one here, it equates actually to about 290 million years after the Big Bang. And so a lot of these images and things, the Hubble had also detected or was aware that they were there, but suddenly the James Webb can analyse it, do some spectroscopy on it. And they found there's a significant amount of oxygen in this galaxy that's only when the universe was only 290 million years old. That tells us that it's quite a mature, relatively mature galaxy. And what do I mean by that? Is the very, very first stars, after the Big Bang, it was really just essentially hydrogen, helium. So the first stars would have just been hydrogen, helium. And we call those population 3 stars, or let's just call them first generation stars. They would have eventually been very large. They would have gone supernova and exploded. But before that, they would have gone through of forging that hydrogen and helium, forging it into your likes of your oxygen, your carbon, your nitrogen, your neon, all those heavy elements get forged inside stars, and that's what stars do. In fact, all the carbon and nitrogen and anything greater than hydrogen and helium in this room was all forged inside stars. So it would have got forged inside those early stars. They went supernova and then enriched the space around them with those those heavier elements like your carbon and oxygen and so on. So when you see a star or galaxy with oxygen in it, that tells you that already you're into your second generation of stars. So it's chemically evolved already. So we know we're not looking at the first generation of stars, certainly by no means in the large numbers. You know that at least a good chunk of them have gone supernova, and you're looking at a lot of second generation stars there. So that was something that was interesting. They were quite surprised at how they're seeing reasonably sized galaxies and reasonably chemically evolved galaxies so early on. That's sort of one of the stuff that they're just working through. But that's invaluable information to understand how the universe developed and evolved to how it is today. I really put some slides up here. The James Webb is used as spectroscopy, the amount of redshift, how much the spectral lines move across, to get a precise estimation of the distances and the compositions to these. And it's got 4 spectroscopes, two main ones here. And the reason I just put this here just to show illustrate the versatility of the James Webb. Your near spectroscopy observes up to 48 individual galaxies, all simultaneously in high resolution. That's pretty impressive considering the distances you're looking over. The nearest, that's a slitless one, so it's more lower resolution, but because it hasn't got a big slit, it allows more light in, and it's able to look at all the galaxies in the entire field of view, including even the most faintest galaxies that you're struggling to look at. It's able to look at all of those, but albeit in low resolution, but it can. So I just put those 2 little interesting points down there just to illustrate the versatility, the ability of this James Webb telescope. It's no ordinary space telescope. So this galaxy here, you can see how the shift, these normal spectral lines would be a little over this way. So they've been moved more towards the left part of the spectrum. There are simple formulas you can use, and that equates to 11.3 billion years ago. And then you move down to the galaxy there. Once again, you can see the spectral lines have all been shifted across. So that's called redshifting, and that equates to 12.6 billion years ago. This galaxy here, you can see the spectral lines have been moved along further. That's 13 billion years ago. And this galaxy here, once again, you can see the spectral lines have been moved right over to that right-hand side there, and that equates to 13.1 billion years ago. So the purpose of that slide was just to show you how versatile it is, what it can do, and how it estimates the distances with precision, and also the composition to these faraway early galaxies. Okay, something that's just done fairly recently is that it's found its first most distant supermassive black hole merger going on. It can pick it up because they're known as quasars, and that's what the central QSO stands for, quasi-stellar object, also known as quasar. A quasar is another name. Essentially, it's a supermassive black hole at the center of a galaxy, but usually it's early on in the galaxy, and they are super powerful, really luminous and bright. They are supermassive black holes on steroids. They are a different beast. They just blast out energy. And it's thought because in the early universe, they had lots of these black holes, supermassive black holes, had a lot more material. The universe was denser and thicker and mergers going on. It had a lot of material to munch on, so naturally it was more active. And they call them quasars. So they picked up here, there's a decent sized galaxy here with a big quasar, in other words a supermassive black hole in its middle. And then there's 2 satellite galaxies, and these guys are all undergoing a merger. So this is one of the very first earliest mergers in the universe they're actually getting to see and analyse. And here they put this codes for the spectroscopy colours. So oxygen is green. Look at all the green, look at all the oxygen through this. Once again, this galaxy is more evolved and it's merging than they thought. They thought, wow, this early on, and we're getting mergers, we're getting mature galaxies, so it is providing insights into the whole rapid process of merging and chemical evolution of these early galaxies and supermassive black holes. And the implications of this is important. Because galaxies and the supermassive black holes in the early universe, as I've mentioned, are much larger and more chemically evolved than they expected. And one of the questions over the years have been these supermassive black holes, millions up to billions of solar masses, how did they form, and how did they get so large so quickly? Particularly when you see that quasar one back here, and I think I mentioned, didn't I? Put in here, I didn't mention it, but I wrote it down. 2 billion solar masses, in other words, 2 billion times the mass of our sun. At this early, when the universe was only 740 billion years after the Big Bang. How did that beast get so big, so early, and is already going through a merging process? Oh, sorry, might be me, yeah. Pardon me, yeah. So, possibilities. What's going on through here? Is it how did these big supermassive black holes form? One is, was it just accumulation of stellar black holes? Just existing, just accumulating together, seeding together to form a supermassive black hole? Was it a star cluster that's just started to collapse onto itself to form a supermassive black hole, and then they just merge and just grew from there just with growth? The computer models suggest that no, that would not have happened in that time frame. So they most likely, from what they see, is that the supermassive holes probably formed from primordial supermassive black holes. What do I mean by that? Primordial meaning from the original, shortly after the original bang of the universe, whereby the universe was just full of hydrogen and helium, and it would have been vast clouds, quantities of cold hydrogen that hadn't been heated yet, that just collapsed in onto itself just to create a supermassive black hole straight up. And it would have had to have had some early mergers in there as well, which they can see. So their observations have been very useful, and no doubt there'll be more coming to try and crack this mystery that's been in astronomy for so long. Okay, and of course, so those are the galaxies. How about single individual stars? And the earliest one there is known as Earendel, which means, in Old English, means early or morning star. And this is the first one. The Hubble had already identified it a couple of years ago, but it was the James Webb was able to have a look at it in a lot more detail and get a spectroscopy of it. And you can see some gravitational lensing. Here it is here. There's Earendel just sitting right there. So they're able to have a closer look at it. That's a distance of 28 billion light years away, or 900 million years after the Big Bang. So the enhanced resolution up to the Hubble just said, look, it's there. James Webb is able to analyse it. They think it actually even could be a binary system. There's some hints of that. But the main star is a massive B-type star, much more massive and hotter and more luminous, probably twice the temperature of our sun, and probably 1 million times more luminous than our sun. It's a big B-type spectral star. Now, the other thing what it has done here is these streaky little red streaks through here. They think these are very, very early open star clusters, so just clusters of stars from in the early stages. So it'd be really great for them to analyse those further. And these two dots here, either side of Earendel, are thought to be really, really early forming globular clusters. Our Milky Way and its halo have these big old stars, 13 billion years old. In other words, right when these were forming, they're like dense, gravitationally bound clusters of stars. There's about 158 of them, all out there. And we don't really know. There's all sorts of theories how they formed, perhaps from superclusters and so on. But anyway, wouldn't it be neat to have a look at these early stages of these globular clusters? And there they are, globular clusters. So they'll analyse those further as well. All this is possible because the James Webb high resolution infrared. Okay, so how about studying the atmosphere of exoplanets? And the idea here is that the James Webb is able to look, can line up where you get a perfect line of an exoplanet going around its host stars, and if the alignment is such that the light from the host star shines through the atmosphere of the exoplanet, the James Webb is able to have a look at its atmosphere and analyse it. And in particular, it's looking for signs of life, or what's in it: water, carbon dioxide, oxygen, and so on. This is one of the very first ones that they did. It was WASP 96b, 1150 light years away. So this is one of the very first ones. It's what they call a hot Jupiter. Very, very close to a star. It was half the mass of Jupiter, but over greater than 1.2 times the diameter. and really, really close. 1/20th, so a 20th of the distance between Earth and our Sun. It's 1/20th right in there. So, and that's the sort of spectrograph that it does, and you can see it showed water vapor, because it was so hot, being a hot Jupiter, so a lot of water vapor. Now, of course, these are the things they look for signs of life. If you can see oxygen in there, that's a good sign of life. If you see water, of course, life likes water. Methane is a strong possibility, not definitive, but possibility of life. Certainly, if you see fluorocarbons there, you know you've got life, you've got some sort of civilized life that are going about destroying their own atmosphere. So pretty much like we're pretty good at doing. So it's a very valuable tool. And so I just want to highlight this with a recent analysis of the atmosphere, possible atmosphere of an exoplanet. So this is exoplanet LHS 1140b, and it's been in orbit around its host star, a red dwarf, 48 light years away. And already the Hubble and one or two other telescopes was aware of it and has identified it. They've estimated it's about 1.5 diameter of Earth. They suggest that it's probably tidally locked around its host star, meaning it's close enough with the gravitational pull is where it rotates at exactly the same pace it's orbiting around, like our moon. So one side of that exoplanet is constantly facing the host planet, one half of it is constantly facing away out into the cold of space. And of course, which means one side is hot, one side is cold. So that's all fine, they'd already worked that out. But the James Webb had a look at it and detected hints. It's very suspicious of an atmosphere going on. And suddenly that changed everything. They know that this must be a rocky planet. They estimate its size by the light curve when it goes in front of its star, how much the light curve, just the light dims down. That tells them the size. Planets, they appear to orbit around the stars. But what actually happens is the star and the planet go around the sort of center point of gravity, the barycenter, which usually is right in the middle of or close to the middle of the star, inside the star. So the planet doesn't orbit, but the star actually wobbles a little bit as it's doing a bit of a dance around that center of gravity. And the precise instruments of these modern day telescopes can pick up the amount of wobble. And from there they can determine the mass of this exoplanet. You know its mass, you know its size, you can work out its density. They know it's a rocky planet, but its overall density was less than it should be. There's only one possibility to explain that: water. It's got loads of water, most likely just covered in big, thick ice sheets, a snowball planet, if you will. Now, here's the game changer. The James Webb picked up some signs of an atmosphere. If there's an atmosphere on there, and if I say to you which it is, this exoplanet is in the habitable zone around its host star. The habitable zone being a zone, the Goldilocks zone, where if you're too close to that star, any water there's going to just boil off and evaporate. Too far out, any of it's going to be ice. But suddenly, if you're in the habitable zone, the right temperature to support liquid water, and you've got an atmosphere that can contain liquid water, the implications of that is this is the first rocky exoplanet in the habitable zone with an atmosphere and possible liquid surface water. And they estimate if this is so, there's enough water in there and the temperatures will be right, whereby there'll be an ocean on that side facing its host star, about the size of the Atlantic Ocean. And what does life like? Water, liquid water. So the implications of this observation from the James Webb is huge. Okay, and I just put a few other little things in there just to add to it. Yeah, it's busy looking at the outer planets within our own solar system. It's not just far away objects. Here's here. It's taken some lovely pictures of the outer planets. This is a lovely picture of Jupiter in high resolution infrared. The detail in there of its atmosphere is just unprecedented. And from there, they hope to improve their understanding how energy is distributed in the different layers of Jupiter's atmosphere. So it's just not all far away astronomy that they're doing either. So that's groundbreaking stuff. Uranus. So on the left there's a 1986 image. That was an image from Voyager 2. One of our best images of Uranus. It looks pretty bland and featureless, doesn't it? But look at the James Webb's image of it, and you can see a complex ring system around it. And notice it's all on its side. Uranus is tipped up, roughly a little bit over 90 degrees on its side, probably from a collision early on in the solar system. So you can see that. But the other thing you can see here, it's got a polar cap, a north polar cap that's facing towards us. Of course, there's no hard surface on Uranus because it's an ice gas planet, but that's probably some very hazy aerosols in the atmosphere that's doing that. It's causing a nice polar cap appearance. So you can see the extra detail they're getting in of studying our own solar system with it. And of course, not the inner planets because it's going to be facing back towards the sun, but yeah, the outer planets, absolutely. The other thing is brown dwarfs. So what are brown dwarfs? Brown dwarfs are the forgotten, the missing link between stars and exoplanets, sort of the forgotten substellar objects they're often called. Stars form by gas clouds collapsing down their own, get really, really hot, and by definition they've got to be hot enough to burn hydrogen to helium in a core. So that's by definition stars, and that's how they form. An exoplanet by definition forms in the disk, protoplanetary disk around a host star. But so you get these objects out there that formed like a star, whereby from a gas cloud that just collapsed down, but they're not hot enough to generate the energy inside them to fuse hydrogen into helium at their cores. So they're out on their own. They're sort of called substellar objects. And there hasn't been a lot known about them, but they're called brown dwarfs. And because they're being relatively faint, they glow mainly in infrared because of the low temperatures, surface temperatures of 200 to 2800. So they glow mainly in the infrared. Hello, James Webb Telescope, infrared observations, high resolution, and it can start identifying them. And the two brown dwarfs, it's a binary system, 6.5 light years away. These are our closest brown dwarfs to Earth. So James Webb is being able to study these, and it's able to probe not only into the atmosphere of these brown dwarfs, but 3 depth of layers down into their atmosphere of what's going on, of regions in the atmosphere, a vertical profile. They conclude, look, there's a lot of hot winds and sands, a lot of silicon, water vapor, carbon monoxide, about 1,000 degrees, such that they can even form. The implications are, this is of course an artist's impression, but the implications are now they can start to get an idea and picture of not only identify these really faint brown dwarfs, but actually get an idea of what's even going on in their atmospheres now. So that's been a huge step forward of studying these very faint, sort of elusive, up till now, objects. Now, the other thing is, I mentioned these exoplanets that form from a disk around its host stars. You can also get rogue planets, in other words, just roaming freely without any attachment to their host star. How did that happen? They would have formed from a disk, but they would have then got ejected, and for whatever, all sorts of reasons, stellar dynamics, would have got booted out of their solar system. So they roam. So they've been aware of them, there's been a few of them been aware of them, but suddenly the James Webb was studying the Orion Nebula, and our closest stellar nebula, and just in the Orion Nebula alone, 540 of these really faint rogue planets they were able to identify. That's 42 of them were pairs. I love the names, the acronyms they come out. So Jupiter mass binary objects, or jumbos. Then astronomers will find an acronym to fit any circumstances. So they found in these jumbos. So the implications here is that if they found 540 of these elusive faint objects, just in Orion's Nebula alone, there's probably billions of them throughout the Milky Way galaxy and other galaxies as well. So that's, that, once again, that's a really important implication. All because it's high resolution and infrared. Okay, so just in a nutshell, it's extremely, what makes it special, it's extremely powerful because of its large mirror, which enables it to see faint, small, distant objects in high resolution. It sees in the infrared, and it's very good at that because of its location, 1.5 million kilometres out into deep space. It's got this specified 5-layer tennis court sized sun shield, gold-plated mirror, specialised detectors and instruments. Cryogenics keeps it really super cool, minus 220 degrees Celsius, such that it really can see through infrared. It can cut through dust. It can see new stars forming, dying stars, early galaxy mergers. It can see see at long distances where wavelengths have been stretched into infrared. So it can see the first stars in the galaxies to better understand how the universe formed and evolved. Suddenly now these exoplanets, it can hunt out atmospheres and look at the atmosphere, see what's in the atmosphere, any telltale signs of life. Solar system outer objects and brown dwarfs and rogue planets. Up till now they've been very elusive objects. Suddenly they're in our scope to study. And if there's one message you take home from today, this is it. The James Webb Space Telescope is changing our view and understanding of the universe, and that's how. So I hope you've enjoyed the James Webb Space Telescope, unique features and discoveries. Thank you very much.